Hello and welcome to the new unit. We are learning about momentum. We're going to start our lesson about momentum by considering a couple things. Let's look at this first box right here, the consider number one. Let's imagine four different scenarios. We have a bowling ball that's rolling at 20 meters per second, a B word that has been SH'd out of a G at 400 meters per second, another bowling ball that's moving at 2 meters per second, and a golf ball that's moving at 50 meters per second. Now, if I asked you which one of these has the most momentum, or kind of like a related question, which one of these would hit the hardest? Which one of these would hurt the most or cause the most damage if they hit something? Um, this is kind of a challenging question because one of the instincts to go with is, well, the bowling balls are very, very massive, and so that's a lot of mass to deal with. But then if we're looking at something like the B word or the golf ball, they're moving much faster, and we know fast-moving objects also have huge potential to cause damage. So it's a little bit of both. It could be one, it could be the other. So the first thing that we need to realize is that when we're talking about momentum, we're not talking about mass or just velocity. We're talking about the two of them together, and they exist in this equation right here, P equals mv. So this is the equation for momentum, but if we're trying to describe it in words, we would just call it the mass in motion. And what's important about both the lesson or the equation and the mathematical definition here is that it doesn't give priority to either one. When you multiply m and v, the product of those is based on how big each number is. So it's not like mass is more important or velocity is more important. They're both equally important, and the product is what gives us the momentum. So a bowling ball is about 5 kilograms. A B word is about 0.005 kilograms. Actually, it's probably even less than that. Probably have to put another zero on there. Um, the bowling ball again is 5 kilograms, and a golf ball I think I worked out was 0.005. Yeah, about 10 times the size of the B word. So for multiplying these out, it works out that we have 5 times 20. This is 100 kilogram meters per second. That's the kilograms times the meters per second. These are the units there of momentum. Momentum either has the units kilograms meters per second, or there's one other thing that we can use for the units that I'll talk about in a sec. Multiplying out the next one, that 400 times the 0.0005. Gosh, I should have done this first, but I think it works out to be 0.02 kilogram meters per second. I may be slightly off, or off by a factor of 10. Feel free to correct me in the YouTube comments if you'd like. This next bowling ball is moving at 10 kilogram meters per second. And then finally, the golf ball, that's going to be 0.25 kilogram meters per second. So it works out that in this case, because the bowling balls were just so massive compared to our other objects, they definitely had the most momentum. But you can see that kind of unexpectedly, the golf ball ended up having more momentum than the B word. I don't know if that actually was unexpected on your end, but given that the B word was moving so fast, there's kind of that feeling that maybe it should have more momentum. So there's the equation for momentum and the key idea. Moving on to our next consideration, let's consider a collision, two different collisions actually. In the first one, we have like a big rig that's coming up behind and hitting a car. In fact, not just any car. Let's have this a Tesla. For no reason at all. It's just a Tesla. So that Tesla is getting hit from behind, but they're both going the same direction. So the big rig's moving 40 meters per second, and then it just hits that Tesla from behind. The other option is we have a head-on collision where the Tesla is coming straight at the big rig. The big rig's still going 40 meters per second, but now the Tesla is going 20 meters per second in the opposite direction, going towards the big rig instead of away. So if we thought about this one here, we're trying to decide, which one of these is going to be the most catastrophic, the biggest collision. The question really is obvious. It's definitely going to be this one here. This one gets the big giant frowny face because there's going to be a pretty devastating accident that happens there. And so one of the takeaways that we want to get from this is that this is a vector quantity. Momentum is a vector that has both direction and magnitude. The magnitude is what we figured out how to calculate in here. For the direction, you're going to need to keep very careful track of what direction it's going, because a lot of questions actually build off of the direction of the momentum. One common question that students mistake is if I have an object that's moving downwards at v that way, and then it bounces and it comes back up with v that way, we want to remember that its change in momentum was not 0. It was actually 2 times mv, because it went from v down to a negative v upwards, which was a change of v because it stopped, and then v the opposite direction going up. I guess based on the coordinate system I just used. Actually, that change is negative 2mv. Okay, so the big idea though here is that this is a vector quantity. So I want you guys to always keep track of the direction it's going. Our final consideration in this box here is, let's imagine we have 4 different boxes that we're pushing, and I have the masses and I have the forces that they're being pushed with. If I asked you, okay, which one of these is going to have the greatest momentum at the end, we're going to have to think through some different pieces to this puzzle. One thing that we could think through is that this object here, oh wait, maybe I didn't say this yet, but we're pushing them all for the exact same amount of time. So I want to know which one of these has the greatest change in momentum by the time we're done. So looking at this one here, if I wanted to figure out its acceleration, it would just be f over m, which those values were given. This one too has an acceleration, but it would be 2f over 2m, 2f over 2m, which works out to be the same acceleration. And then our last one, we have an acceleration of 2f over m. So we can see that there's different accelerations coming out of here, but that doesn't yet give us the full answer for what's going to happen here. In fact, I'll show you in a sec, but it's going to turn out that these two are going to have tie for the greatest change in momentum. And then this one down here at the very top is going to have the lowest momentum. So the reason for that is if we're looking at changes of momentum, that would be a change in momentum. We can look at it as m delta v, or we could just look at it as m delta v, the mass times the change in velocity. These things started at 0 and then they accelerated. And so our next piece is we could think about that in a slightly different way, where we could say, well, instead of delta v is really delta v over delta t is equal to acceleration. So acceleration times delta t would be equal to delta v. So I can put that in there, and I can say m a times delta t is equal to the change in momentum. And then the final piece that I could put in there is I could get rid of, I could change m and a and treat that as the net force acting on it. So then the net force times delta t is the same thing as the change in momentum. So that was a math proof. I accidentally got more mathy in there than I meant to when I started the video. But this quantity here that we can call change of momentum, it has another name, and that other name is impulse. So impulse is how quickly or how much the momentum changes, and there's 2 ways to calculate it. The first way that we can calculate it is right here. We can just figure out what the change in momentum is, or if we know the net force and we know the time that it's being applied, we can figure out the impulse. So going back up here, we know this one had F applied over T, so this one would be Ft, and this one would be 2Ft and 2Ft. So based on that, both of these have the greatest change of momentum, double the other one. Now the reason, it's still interesting because we have these differences in accelerations and same accelerations going on. But if we're comparing the first one and the second one, while they do have the same acceleration and they will end up with the same velocity after the same period of time, The second one is more mass moving that same velocity, so that'd be more momentum. Then for the second and third one, the third one ends up accelerating twice as fast, so it would be going twice the speed, but it has half the mass. So its momentum ends up being the same as the slower but more massive object that's the second one on this list. So that's the idea of impulse. The last piece that I want to put on here is the units. I already said that the units of momentum are kgm over s, kilogram meters per second. We can also write them as, coming from right here, newtons times seconds. Now that totally works out because a newton is a kilogram meter per second squared. So if I multiply that by seconds, it ends up just being a kilogram meter per second, which is the same thing we said it was over here. But both of those get used as the units for momentum and impulse. So just be aware that if you see those, you're seeing something that's talking about momentum, or you're seeing something that's talking about impulse. And just be aware that that's the kind of question you're looking at. So that should be everything you need to know to get introduced, to get started with momentum. Thank you for watching the video. I hope this helped.